Have you ever wondered why fire feels hot, or why ice melts on its own? Today we'll explore the hidden energy rules governing these phenomena, Enthalpy and entropy. By the end, you'll see how these concepts explain everything from car engines to why your room gets messy. Hey there, welcome to my channel. Before we begin, remember to hit subscribe so you never miss out on new videos. Let's jump right in. Part 1. Enthalpy, the heat accountant. Enthalpy is a property that shows the amount of heat in a system. For example, when you mix hot chocolate powder and hot water together, the hot chocolate powder has higher enthalpy than the water because it has more energy. So they must be mixing to get to some kind of equilibrium. Now, when chemicals react, their enthalpy changes, which we call the change in enthalpy, or heat of reaction. Think of it as a heat bank account for the reaction. When the account goes down, heat is released. When the account goes up, heat is absorbed. The formula for enthalpy is pretty straightforward. H equals U plus PV. U stands for internal energy, which is the sum of the kinetic and potential energy of the molecules. And PV stands for pressure times volume, or work done by the gas pushing against the walls of the container. Work is measured in the same units as energy, so they can be added together. In reality, H only changes when the amount of matter in the system changes. But for now, just know that H is the heat gained or lost by a reaction. Here's a real-world example. Gasoline burning in a car engine. This reaction releases heat and light, making it exothermic and spontaneous. The value of the change in enthalpy for the combustion of 1 mole of gasoline is negative 5,471 kilojoules per mole. A kilojoule is a unit of energy equal to 1,000 joules. The negative sign means that heat is released during the reaction. Now let's do a quick demo. Light a match and ask the audience to feel the heat coming off the matchstick. Notice how the matchstick burns brightly and then goes out after a few seconds? That's because the supply of gasoline runs out. Now let's look at another example. When an instant ice pack is activated, ammonium nitrate dissolves in water and the solution gets colder. This reaction is endothermic, meaning it absorbs heat from its surroundings. So an ice pack is a great example of an endothermic reaction. The forward reaction shown here absorbs 28.3 kilojoules of energy for every 1 mole of ammonium nitrate that dissolves. The sign of the change in enthalpy is positive, which tells us that the reaction is endothermic. So to summarize, when you have a negative change in enthalpy, it is exothermic and heat is released. But when you have a positive change in enthalpy, it is endothermic and heat is absorbed. Part 2. Entropy. The chaos controller. Entropy measures disorder. Things tend to go from order to disorder. You can even think of entropy as a measure of randomness. The more ways a system can be arranged, the higher the entropy. For example, imagine having 6 cookies in a jar. At first, you could have them all lined up perfectly, but there are many more ways to arrange them so that they're mixed up. Therefore, the mixed-up version has higher entropy. This idea was formalized by Ludwig Boltzmann, who came up with the following equation for calculating entropy. S equals Kb times the natural log of omega. S represents entropy. Kb is a constant called Boltzmann's constant, and omega is the number of possible arrangements of a system. In chemistry, we typically deal with moles instead of individual molecules. So a modified version of the formula is used where omega is replaced by the number of microstates. Microstate is a particular arrangement of molecules. The more microstates a system has, the higher the entropy. Now, when chemicals react, their entropy changes, which we call the change in entropy, or entropy of mixing. In general, the change in entropy of a system can be calculated by taking the number of microstates of the products and subtracting the number of microstates of the reactants. Here's a real-world example. When ice melts into water, entropy increases because the molecules have more freedom to move around. They transition from a highly ordered solid to a less ordered liquid. Another example is when perfume spreads throughout a room. The gas molecules disperse randomly, increasing the disorder of the system. This increase in entropy makes the process spontaneous. To summarize, when the change in entropy is greater than 0, the reaction is spontaneous. Now let's look at some examples of decreasing entropy, which requires energy. When water reaches its freezing point, it transitions from a liquid to a solid, resulting in a decrease in entropy. This process is not spontaneous at normal conditions, because it would require energy to decrease the disorder of the system. Another example is when DNA is formed from individual nucleotides. Cells use energy to build this highly ordered molecule. So to recap, when the change in entropy is less than zero, the reaction is not spontaneous. We have to put energy into it. Now let me leave you with a question. Why doesn't a broken egg unscramble itself? Answer: reversing this process would decrease entropy, which requires energy. Part 3. Gibbs free energy, the spontaneity judge. Gibbs free energy takes both enthalpy and entropy into account to determine whether a reaction will occur. Mathematically, the change in Gibbs free energy is calculated as follows. Delta G equals delta H minus Tp's, where T is the temperature in Kelvin. So if you want to figure out if a reaction will occur, you can use the change in Gibbs free energy. If the value of G is less than 0, the reaction is spontaneous. However, if the value of G is greater than 0, the reaction is non-spontaneous. Let's consider the rusting of iron as an example. Rusting occurs when iron reacts with oxygen in the presence of water to form iron oxide. The reaction is exothermic and releases heat. Additionally, the products have more disorder than the reactants, meaning entropy increases. Since the values of both delta H and TPS are negative, the reaction is spontaneous at low temperatures. Now let's take a look at the opposite case. Water freezing at 25 degrees Celsius. This process is endothermic and absorbs heat. Additionally, the products have less disorder than the reactants, meaning entropy decreases. So in this case, H is positive and TPS is negative. Since the values of delta H and TPS have opposite signs, the reaction may or may not be spontaneous, depending on the relative magnitudes of the two values. To summarize, when the change in Gibbs free energy is less than 0, the reaction is spontaneous. However, when the change in Gibbs free energy is greater than 0, the reaction is non-spontaneous. To better understand the spontaneity of chemical reactions, let's look at two case studies. First, wood burning. When wood burns, it reacts with oxygen to produce carbon dioxide, water, and ash. The burning process releases heat and light, making it exothermic. Also, the products are more disordered than the reactants, since gases are produced. Both of these factors make the combustion of wood spontaneous. Next, photosynthesis. Plants use energy from the sun to convert carbon dioxide and water into glucose and oxygen. This process is endothermic because it absorbs light energy. Additionally, glucose is a highly ordered molecule compared to carbon dioxide and water. These factors make photosynthesis non-spontaneous under standard conditions. However, plants are able to overcome the unfavorable entropy change by harnessing energy from sunlight. Now let's do a quick demo to show the difference between an exothermic and endothermic reaction. Here we have a glow stick. The reaction inside the glow stick is both exothermic and spontaneous, so it will glow without any additional energy input. Now here's a volcano made from baking soda and vinegar. The reaction is endothermic, so it won't get hotter, but it is spontaneous because the products are more disordered than the reactants. Now, let's wrap things up. Enthalpy and entropy are two important concepts that help us understand the spontaneity of chemical reactions. Enthalpy refers to the heat of the reaction, while entropy refers to the disorder of the system. The change in Gibbs free energy takes both enthalpy and entropy into account to determine whether a reaction will occur. To recap, enthalpy refers to the heat of the reaction. Entropy refers to the disorder of the system. And Gibbs free energy predicts the spontaneity of a reaction. In the end, we saw that entropy wins every time. Your room is a great example of this. Even though cleaning your room is a positive change in entropy, it requires a lot of energy. Without external energy input, your room will always get messier. So what will you choose? Will you burn gasoline for its negative H, or melt ice for its positive S? Let me know in the comments section below. And don't forget to like this video if you enjoyed it. Thanks for watching.